Hello everyone, I am Meenakshi, the student of BSc Chemistry Honors. Today, I am going to read a chapter of inorganic chemistry named Chemistry of Noble Gases for the visually impaired students. So let's start. Group 18 of the periodic table consists of 6 elements: helium, neon, argon, krypton, xenon, and radon. This is a unique group as all its members are gases at ordinary temperature and pressure. Prior to 1962, the elements of this group were known as inert or rare gases. Today, both the names have been proved wrong. This is because these gases are no more rare now, as these are found in the atmosphere, although only argon is present in high proportion. Some of these gases, especially xenon and radon, have been found to be reactive, and accordingly, we can no longer call them as inert gases. These gases have been correctly named now as noble gases in view of their reluctance to react with everything. In fact, the noble gases make up the least reactive group of the periodic table. Position of the noble gases in the periodic table. Mendeleev arranged all the known elements in the form of a table known as periodic table in 1869 on the basis of physical and chemical properties of the elements. The noble gases were not known at the time. As the result, no place could be allocated to these gases. Later on, when these gases were discovered and characterized, it was thought to position these gases in the periodic table on the basis of their physical and chemical properties. It is curious to note that these gases are not reactive at all on the basis of their atomic mass and non-reactive nature. Ramsay, the main inventor of these gases, proposed altogether a new group called the zero group for these gases. The group zero suggests extreme inactivity or zero valency of the noble gases. Prior to the discovery of noble gases, the elements happened to be arranged in a manner that all the electropositive elements were placed on the extreme left of the periodic table and the electronegative elements on the extreme right of the periodic table. Thus, one can sense a very sudden change in the properties from the most electronegative halogens to the most electropositive alkali metals. Now, the inclusion of these gases in between the halogens and the alkali metal appears justified, as these gases have neither electronegative or nor electropositive character. The position of these gases was finally confirmed by Moseley, who suggests atomic number as the basis of classification of elements in the modern periodic table. These gases now happily enjoy the last column on the extreme right of the long form of the periodic table. Discovery of the noble gases. Helium was detected for the first time in the spectrum of Sun in 1869. It was nearly 30 years later when Ramsay found the helium as a gas given off from a radioactive uranium source. The discovery of argon was made by Lord Rayleigh by measuring carefully the density of nitrogen sample from different sources. He observed that the nitrogen sample from air was always denser than that obtained from the decomposition of ammonia. It is interesting to note that when Ramsay burned magnesium in nitrogen from air, he found a small amount of gas which was identical to that found by Rayleigh. He named this gas as argon. It comes from the Greek word argos for the ideal one. The other three gases were obtained by the fractional distillation of liquid air and were named neon, the new one, krypton, the hidden one, xenon, danger. The name radon comes from its radioactivity. William Ramsay and Lord Rayleigh were the main contributors for the discovery of inert gases, and both of them were decorated with the Nobel Prize in 1904. Helium. Helium was discovered by Sir William Ramsay. Neon, argon, krypton, xenon was also discovered by Sir William Ramsay. But there was a great role of Lord Rayleigh in the discovery of argon, and radon was discovered by Frederick Doll. Electronic configuration. The electronic configuration of these elements of noble gases. Helium, the first element of the noble gases, have an electronic configuration 1s2, whereas all the other elements have a general electronic configuration ns2 and p6, where n is the period number. Thus, all the noble gases with the exception of helium, have 8 electrons in their valence shell. All the elements of noble gases are placed in group 18 of the periodic table. It is a unique group where all the members are colorless, odorless, and monoatomic gases at room temperature. The monoatomic state of these gases is due to the stable configuration of their atoms. All these gases occur in the atmosphere. It is interesting to note that the total volume of the noble gases come close to 1/20th of the volume of air. These gases neither burn nor support combustion. In fact, these gases constitute the least reactive group in the periodic table. Atomic radii. The atomic radii of the noble gases increases from helium to xenon as one moves from top to bottom in a group. This is because when moving from one atom to another in a group, there is an increase in the principal quantum number. As the result, new shells are being added and electron clouds expand. The atoms of the normal gases are held together by van der Waals forces. These forces are very weak. To give you an idea, let us consider the bond energy of normal ionic or covalent bond compared to the bond energy in a system where van der Waals forces are operative. The bond energy in the former varies from 100 to 500 kJ per mole, whereas in the latter case it varies from 5 to 50 kJ per mole. The atoms of the noble gases are held together for at the longer distances. It is therefore important to mention that in case of noble gases, one should talk of van der Waals radii rather than covalent radii. This is because noble gases do not form covalent bonds but are held together by van der Waals forces. Ionization energy. The first ionization energy of noble gases are very high. This is primarily because the completely filled electronic configuration. However, within the group, the ionization energy decreases down the group from helium to radon because of increase in atomic radii. Electron affinity. The electron affinity of noble gases are nearly zero because of their stable electronic configuration. It clearly suggests that the noble gases have no tendency to accept the electrons. Melting and boiling point. The melting and boiling point of noble gases are very low. This is because the atoms of these elements are held together by weak van der Waals forces of attraction both in liquid as well as in solid state. An inspection of table reveals that down the group from helium to radon, the melting and boiling point of these elements show a regular increase due to the corresponding increase in the magnitude of their van der Waals forces with increase in size of atom. Solubility in water. The normal gases are slightly soluble in water. The solubility has been found to increase down the group from helium to radon. Ease of the liquefaction. These gases are not easily liquefiable. The ease of liquefaction of a gas depends upon the magnitude of attractive forces present in the atoms or the molecules. Since these gases are held together by weak van der Waals forces, these cannot be easily liquefied. However, as the atomic size increases, the magnitude of van der Waals forces increase, and thus the ease of liquefaction increases as one moves down the group from helium to radon. Chemical properties of the noble gases. After the discovery of noble gases, many attempts were made to prepare the compound of these elements. However, all the attempts were unsuccessful and the elements were compelled to be known as inert gases. The inertness of these elements to chemical reactivity is attributed to the stable closed shell electronic configuration Ns2np6 of the noble gases, excepting helium, which has the configuration 1s2. The high first ionization of energies of noble gases. Nearly zero electron affinity of noble gases. On the basis of above facts, noble gases do not have any tendency to lose, gain, or share electrons with other atoms. The first compound of the noble gases was prepared by British-born Canadian chemist Neil Bartlett in 1962. In fact, the Bartlett was studying the reaction of platinum 6 fluoride (PTF6), which is a red crystalline solid. He observed that when PTF6 is exposed to the molecular oxygen, a yellow ionic solid of composition O2 positive, PTF6 negative is formed. The reaction cause O2 gas reacts with PTF6, which is red in color, and gives rise to dioxygenyl hexafluoroplatinate 5. The above reaction clearly demonstrates that the oxygen gas has been oxidized. thus suggesting the high oxidizing character of platinum 6 fluoride. While teaching a first year chemistry classes, Bartlett noticed that the first ionization energy of xenon gas was almost identical to that of dioxygen molecule. This makes Bartlett to think that the PTF6 can remove an electron from oxygen. It should be able to remove the electron from xenon atom. He therefore predicted the reaction between xenon and platinum 6 fluoride to form xenon Xe positive PTF6 negative. The Barrett carried out the reaction and found the gaseous xenon reacts with red vapors of PTF6 to give a yellow solid of composition Xe positive PTF6 negative. This marked the first preparation of the compound of the group 18, breaking all the old myths that these elements are inert. Bartlett's discovery opened a new field of chemistry, and within months, scientists prepared fluorides of xenon named xenon difluoride, xenon tetrafluoride. Among these noble gases, xenon is known to form maximum number of compounds, whereas krypton form only a small number of compounds. Before we discuss the chemistry of noble gases, it is important to answer some curious questions, which are: what are the factors that are responsible for the discovery of compound of these gases, and why does xenon form maximum number of compound with fluorine and oxygen? The late discovery of compound of noble gases. Before 1962, it was believed that the noble gases were not reactive at all. This was attributed to the high first ionization potential and nearly zero electron affinity of these gases. All the attempts to prepare the compound of these gases were not met with success. It is interesting to note that the William Ramsay sent a sample of argon to a French chemist, Henri Moissan, to see whether argon reacts with fluorine. Moissan found that there was no reaction between fluorine and argon. This led Ramsay to conclude that the noble gases are chemically inert. On the basis of the chemical inertness of noble gases, Lewis in 1916 formulated the important rule. We today call it as octet rule. According to this rule, when an atom forms a compound, it either gains or loses or share electron to obtain 8 electron in its valence shell. You should remember that the octet refers to a valence shell containing 8 electrons. Compounds of xenon. The historical reaction of xenon gas with platinum 6 fluoride marked the first chemical compound of xenon. If you recall, Neil Bartlett discovered this reaction in the year of 1962. Thus, xenon was credited the first and foremost element of the noble gases to open a field of chemistry called chemistry of noble gases. Today, we have a very rich and interesting chemistry of xenon compound with high electronegativity elements over the groups, in addition to some compounds of krypton. Of all the electronegative elements known, fluorine is the most electronegative. It is able to stabilize the high oxidizing noble gas compound. Now, we are all set to discuss the chemistry and important property of compound of xenon in particular and noble gases in general. Xenon compound, xenon difluoride. Xenon difluoride preparation. It can be prepared by the following methods. Xenon difluoride is the best prepared in the laboratory by heating xenon and fluorine in the molar ratio 2:1 at 400 degree Celsius temperature. Xenon is always taken in excess to avoid the formation of xenon tetrafluoride. Xenon plus fluorine in the presence of nickel at 400 degrees Celsius gives xenon difluoride. It can be prepared by subjecting a mixture of xenon and fluorine in the molar ratio 2:1 to electric discharge. It can be prepared in quantitative yield by reacting xenon with oxygen dioxygen difluoride at low temperature in nickel or the Monell's vessel. Xenon reacts with O2F2 at minus 80 degrees Celsius gives xenon difluoride and oxygen. Properties. Xenon difluoride is a colorless crystalline solid which melts sharp at 129 degrees Celsius. It dissolves completely in anhydrous hydrogen fluoride without any reaction. It gets reduced to xenon with hydrogen. Xenon difluoride reacts with hydrogen gives xenon plus 2HF. It is soluble in water but undergoes slow hydrolysis to produce xenon gas. It gives substitution reaction with strong protonic acids. It reacts with sulfur trioxide to give xenon. Xenon difluoride reacts with sulfur trioxide gives xenon plus peroxy disulfuryl difluoride. Xenon difluoride is a very clean fluorinating agent and it fluorinates double bond in the organic compound. Xenon difluoride reacts with ethene gives CH2F plus xenon. It is a strong oxidizing agent. It reacts with iodine in the presence of fluorine ion acceptor to give IF. It reacts with covalent pentafluorides such as antimony fluoride, arsenic fluoride to form two types of solid compound in which xenon difluoride act as a fluoride ion donor. For example, when the reaction is carried out in 1:1 molar ratio, the reaction occurs. Xenon difluoride reacts with MF2, gives xenon difluoride MF5. These compounds have been established to contain ionic species xenon fluoride positive MF6 negative. The similarly, when the reaction is carried out in 1:2 molar ratio, a compound of composition XeF2 2MF5 is formed. The compound XeF22SbF5 has been shown to contain XeF positive SbF11 negative ions. The ions are strongly bonded to Sb2F11 negative through fluorine bridging as shown. Xenon difluoride has also been shown to react in 2:1 molar ratio as xenon difluoride. Two molecules of xenon difluoride react with arsenic pentafluoride gives 2XeF2AsF5. This compound is conceptually equivalent to Xe2F3 positive AsF6 negative. The ions Xcf3 positive has the expected linear geometry around the xenon and angular geometry at the central fluorine atom. Xenon difluoride in anhydrous hydrogen fluoride react readily with platinum metal and sulfur powder and iridium to produce the highest fluoride according as Pt reacts with xenon difluoride in presence of HF give PtF6 and 3 molecules of xenon. Shape and structure of xenon difluoride. On the basis of the infrared and Raman spectroscopy, the geometry of xenon difluoride has been established. The geometry of xenon difluoride can also be explained on the basis of valence bond theory. The shell electronic configuration of xenon in group state is 5s2 5p6 upon excitation 1 of the 3 5p electron. It is promoted to 5d orbital that result in two unpaired electron, one in 5p, other in 5d. Now 1 5s, 3 5p and 1 5d hybridized to give 5 sp3 3d1 hybridized orbital that are directed to a trigonal bipyramidal geometry. The two orbitals which are singly occupied are used by fluorine atoms to form two xenon fluorine bond, whereas the other three orbitals contain electron pairs. The two xenon fluorine bond lie in a straight line where the three lone pairs of the electrons occupy equatorial position. Xenon difluoride possess a linear geometry xenon 4 compound xenon tetrafluoride. Preparation. It can be conveniently prepared by heating a mixture of gases xenon and fluorine in the molar ratio 1:5 at 400 degrees Celsius temperature under a pressure of 5 to 6 atmosphere. This reaction is ideally conducted in nickel containers. Xenon reacts with F2 gives xenon tetrafluoride. Xenon tetrafluoride can also be prepared cleanly by passing an electric discharge through a mixture of xenon and fluorine in a molar ratio 1:2 at low temperature and low pressure. It is a colorless, crystalline solid with melting point 117 degrees Celsius. It is quantitatively reduced by hydrogen gas. It is a strong oxidizing agent. It oxidizes potassium iodide to iodine. It is a stronger fluorinating agent than the xenon difluoride. It can fluorinate both elements and compounds. It reacts with boron trichloride to form boron trifluoride. It is readily hydrolyzed by water, giving xenon trioxide. However, if the reaction is carried out at -80 degrees Celsius, it results in the formation of xenon oxyfluoride. Xenon tetrafluoride reacts with water at -80 degrees Celsius, gives xenon oxyfluoride. It readily forms addition compound with pentafluoride of phosphorus, arsenic, antimony of composition XeF2MF5 and XeF2 2MF5. XeF4 reacts with SbF5 gives XeF4 SbF5 containing the ions XeF3 positive SbF6 negative. XeF3 positive has a T-shaped trigonal bipyramidal structure. The structure and bonding of xenon tetrafluoride. Spectroscopic studies have shown that xenon tetrafluoride has a square planar structure. The valence bond description of xenon tetrafluoride can be easily explained on the basis of electronic configuration of xenon atom. Xenon atom in the ground state has 5s2 5p6 in the outer electronic configuration. On the excitation, 2 of the 5p electrons are promoted to 5d orbital so that there are 4 unpaired electrons as shown in figure. All a total of 6 electrons, 1 5s, 3 5p and 2 5d intermix to give 6 sp3d2 hybridized orbital. These orbitals are directed towards the corners of a octahedral. 4 of the hybrid orbital containing the single electron overlap with 2p orbitals of fluorine to form xenon fluorine sigma bonds. The other two positions are occupied by lone pairs. Square planar shape and geometry is octahedral. Xenon oxyfluoride. XeOF2. Preparation. Xenon oxyfluoride is prepared by partial hydrolysis of xenon 4-fluoride at minus 80 degrees Celsius. The structure of this molecule is T-shaped. The structure can also be explained on the basis of VBT. The outer ground state electronic configuration of xenon is 5s2 5p6. In order to account for bonding, 2 of the 5p electrons are permitted to vacant d orbitals. In this case, the 5 orbitals 1 5s, 3 5p, 1 5d intermix to give 5sp3d1 hybridized orbital. It is important to note one singly filled 5d orbital is left unhybridized for pi bonding. 3 of the singly filled 5 hybrid orbital overlap with 2 fluorine and 1 oxygen atom to form 3 sigma bonds. 2 xenon fluoride and 1 xenon oxygen bond. On the unhybridized 5d orbital is one of the unhybridized 5d orbital is used in forming an additional bond with oxygen by sidewise overlapping in a pi bond. Thus, xenon oxyfluoride there is double bond between xenon and oxygen in addition to two xenon fluorine single bonds. There are two lone pairs of the electron on xenon atom. Because of the presence of lone pair of electron, there is a mutual repulsion between the bonding and non-bonding pair of electrons, and consequently there is a distortion in the geometry. Thus, xenon oxidifluoride acquires a T-shaped structure. Xenon hexafluoride. The best method of the preparation is by heating xenon gas with a large excess of fluorine in the ratio 1:20 at 300 degrees Celsius under 50 atmospheric pressure in a nickel vessel. Xenon reacts with fluorine at 300 degrees Celsius temperature gives xenon hexafluoride. It can also be prepared by reaction of xenon tetrafluoride with O2F2 at low temperature. Properties. It is a colorless solid with a melting point of 49.5 degrees Celsius. It is the most volatile of all fluorides of xenon. In the vapor state, it is greenish yellow in color. It reacts readily with water to form xenon trioxide, which is powerful explosive. It is extremely reactive towards glass or quartz and produces the dangerously explosive xenon trioxide. This is the reason that the preparation of xenon hexafluoride is always carried in the nickel vessel. It reacts with pentafluoride of phosphorus, arsenic, antimony, and platinum and form a stable compounds. Xenon hexafluoride reacts with MF5 gives xenon hexafluoride XeF6.MF5. The XeF5 positive in the compound have been shown to have square pyramidal geometry. It reacts with alkali metal fluorides to form heptafluorooxygenates. Alkali metal fluorides are well-known fluoride ion donors. It is reduced to xenon upon reaction with hydrogen, ammonia, and hydrogen fluoride. Shape and structure of xenon hexafluoride. The valence bond description of xenon hexafluoride can be explained by considering the electronic configuration of xenon atom. The ground state outer electronic configuration of xenon is 5s2 5p6. On excitation, 3 of the 5p electrons are promoted to vacant d orbital so that there are 6 unpaired electrons available. Thus, a total of 7 orbitals 1 5s 3 5p 3 5d hybridized to produce 7 sp3d3 hybrid orbitals. 6 of the singly occupied orbitals are used for bonding with 6 fluorine atoms. The 7th orbital contains a lone pair. The distribution of 7 hybridized orbitals should give a pentagonal bipyramidal geometry. However, xenon hexafluoride molecule is a distorted octahedral structure. This can be explained if all the 6 positions are occupied by the fluorine atoms and the lone pair is present at the center of the 6 triangular faces. This type of octahedron is known as capped octahedron. Next is xenon oxytetrafluoride. Preparation. It can be prepared by partial hydrolysis of xenon hexafluoride. It can also be prepared by the controlled reaction of xenon hexafluoride with silicon dioxide at low temperature. It can be conveniently prepared by heating a mixture of xenon and fluorine in the molar ratio 1:5 in the presence of excess of oxygen. Properties. It is a colorless compound with a melting point of -46 degrees Celsius. It reacts with water and silica to form xenon dioxide which further reacts with water to give xenon trioxide, which is explosive. It is reduced by hydrogen gas to form xenon. Structure and bonding. Xenon atom has an outer electronic configuration of 5s2 5p6. In order to justify the bonding around the xenon in xenon oxytetrafluoride, electrons sitting in p orbital have to be promoted to vacant 3d orbitals as shown in figure. 1 5s 3 5p and 2 5d orbital intermix to form 6 sp3d2 hybrid orbitals, which are directed towards the corners of a octahedral. One of the 5d orbital remain unhybridized. Thus, the formation of xenon oxytetrafluoride, 5 of the singly hybridized orbital of xenon overlap with singly fill orbital of 4 fluorine atom and 1 oxygen atom to form 4 xenon fluorine single bond and 1 xenon oxygen single bond. The unhybrid 5d orbital of the xenon form a pi bond with the oxygen atom. Thus, the single xenon oxygen bond becomes double and the molecule acquire a square pyramidal structure. Xenon dioxide difluoride. It is prepared by mixing xenon trioxide with xenon oxytetrafluoride at low temperature. It can also be prepared when xenon oxytetrafluoride is either hydrolyzed by water or made to react with silica. It is a colorless solid. It melts at 30.6 degrees Celsius. It gets easily hydrolyzed with water to give xenon trioxide. Structure and bonding. The valence bond structure suggests trigonal bipyramidal geometry with one equatorial position occupied by a lone pair of electrons. The bonding can be explained as discussed in the case of xenon oxidifluoride. Xenon trioxide. Xenon trioxide can be prepared by complete hydrolysis of either xenon 4 fluoride or xenon 6 fluoride as xenon tetrafluoride reacts with water gives xenon trioxide, xenon HF and O2. During the experiments of xenon hexafluoride, several explosions have occurred because the hydrolysis of xenon hexafluoride to xenon trioxide. This reaction can be controlled by carrying out the reaction at low temperature wherein the hydrolysis process stepwise. As xenon hexafluoride reacts with water gives xenon oxytetrafluoride, then it gives xenon dioxide and then it gives xenon trioxide. Properties. Xenon trioxide is a white non-volatile solid. It dissolves readily in water but explodes violently in dry state. It is therefore advised to keep it in dissolved form. It is not ionized in solution and concentration is as high as 4 molar can be prepared. In alkaline solution, it behaves as a weak acid and exists as a xenate ion HXeO4 negative form, which sodium salt can precipitate as NaHXeO4 1.5H2O. The aqueous xenate ions slowly disproportionate to paraxenate and xenon gas. It is one of the strongest oxidizing agent known in aqueous medium. In its oxidizing reaction, xenon trioxide releases xenon gas. It reacts with potassium iodide and liberates 3 moles of iodine per mole of xenon trioxide. It reacts with xenon hexafluoride and xenon oxytetrafluoride. It reacts with xenon hexafluoride gives xenon oxytetrafluoride, and it reacts with xenon oxytetrafluoride and gives xenon dioxydifluoride. Structure and shape of xenon trioxide. The outer electronic configuration of xenon is 5s2 5p6, which has no unpaired electron. In the formation of xenon trioxide, it is anticipated to have 6 unpaired electrons on xenon atom. This could be accomplished by exciting 3 of the 5p electrons to higher vacant d orbitals. 1 5s and 3 5p hybridized orbitals to form 4 sp3 hybrid orbital, which are directed towards the 4 corners of the tetrahedrons. One can see that there are 3 electrons on xenon that remain unhybridized. 3 of the 4 hybridized orbitals, which are singly occupied, overlap with one of the singly filled, the 2p orbital of oxygen, and form 3 sigma bond. The 3 unhybridized orbital of xenon overlap sidewise with 2p orbitals of 3 oxygens and form double bond. It is important to note that one of the hybrid orbital contain a lone pair of electron. As the result, the molecule has pyramidal geometry in place of tetrahedron. Xenon tetraoxide. Xenon perxenate. NaXeO3 when treated with concentrated sulfuric acid gives xenon tetraoxide. It is a yellow volatile, highly unstable solid. It decomposes explosively in the solid state, even at a temperature as low as -40 degrees Celsius. Compounds of other noble gases. Of all the noble gases, it is the chemistry of xenon that has been studied in detail because of its reactivity towards highly electronegative element, namely fluorine. It is the only recently that krypton and radon have been shown to react with fluorine to yield krypton difluoride and krypton tetrafluoride and radon difluoride. Krypton difluoride deserves a special mention. It can be prepared by reacting krypton with fluorine at low temperature in the presence of gamma rays. It is a colorless solid and get easily hydrolyzed. It has been found to be very clean fluorinating agent, and the structure of krypton difluoride has been shown to be linear, which can be easily explained on the basis of its sp3d1 hybridization. Radon difluoride has been prepared, but it is highly unstable. No compound of helium and neon has been prepared so far. This is primarily because of their very high ionization potential as compared to xenon and krypton. In addition, there are no vacant d orbitals in the helium and neon, whereas s and p orbitals of these gases can be promoted favorably. Thank you very much. Here we are done with the chemistry of noble gases and the compounds that are formed by the noble gases. Thank you.